Hello and greetings from Reutlingen and from Bosch Sensortec. I'm Johannes Classen, Technology Manager of Bosch Sensortec, and I'll be happy to guide through this talk here. I would have definitely preferred to do it face-to-face, like probably most of you, but of course that's not feasible at the moment, so let's make the best out of it. I will turn off the camera now so that you don't get distracted.
In this talk, I will provide you an overview of the evolution of inertial measurement units that we have developed especially for consumer electronics. I will start with a company and market overview. Don't be afraid, it won't be too long, even though this is a talk from industry. And then we will dive into the technical part. I will show you the product and system concepts of 3 IMU generations, which are listed here. That we have developed in the last decade. I will talk about progress in MEMS design and in MEMS technology that we have achieved during this time, and I will also show you some key performance parameters. And finally, in the last part, I'm going to talk about what we think are important success factors in this business, and I will give you an outlook of what will be relevant in the future for inertial sensors. So let's get started with the company and market overview. As most of you will know, Bosch has been a pioneer in MEMS with many in-house MEMS technologies. And also basically since 1995, we have been continuously one of the market leaders in MEMS. Some of you may not precisely know what the difference between Bosch and Bosch Sensortec is. So Bosch Sensortec is Bosch fully owned, 100% subsidiary. But at Bosch Sensortec, we are focusing on the development of MEMS sensors and solutions for the consumer electronics market, whereas the mother company is mainly doing the MEMS and sensors business for automotive applications. But there is a lot of synergy and sharing of resources, methods, and processes. So we are really tightly connected. Here is an overview of the company history and of several milestones that we have achieved in the past years. Bosch Sensortec was founded in 2005. Since then, it is quite impressive to see how the number of sensors that have been produced has gone up. So in 2008, it was still only 1 billion, including all automotive sensors. In 2015, already 5 billion, and in 2018, 10 billion. In the lower half, you see some product-related facts. We started the consumer business with acceleration sensors and then developed pressure sensors for the consumer market. Then in 2012, we brought the first IMU to market. In 2014, the first low-power IMU, and then in 2018, the second generation of low-power IMUs. Well, although there is a lot of other interesting things listed here on the slide, I will focus now in this talk on these 3 blue marked IMU generations. To give you some impression of the size of the markets that we are operating in, this graph gives an overview of the consumer electronics MEMS motion sensors market as it is seen by the market analysts of Omdia. Please note that the definition of motion sensors here is a bit unusual because not only accelerometers, gyroscopes, and IMUs are included, but also magnetometers and pressure sensors. Anyway, in total, it is $1 billion+ market. And as you can see, the market is quite strongly dominated by 3 big players, Bosch, STM, and TDK InvenSense. And as you can also see, we have been quite successful in the last years in gaining market shares. Here is an overview of the markets and use cases that we are serving with our sensors. The dominant and most important market in terms of sales numbers and also revenues is still the smartphone and tablets market, followed by the wearables and hearables market. Wearables mainly cover smartwatches and fitness trackers, whereas the most relevant product group in the hearables market are wireless Bluetooth connected earbuds. There are other interesting markets, still not as big as the ones just mentioned, but some of them with rather high growth rates and therefore highly relevant already now and especially in the future. but I will not dig deeper into this here as we want to spend some time now on the technical stuff. Okay, so now let's have a deeper look at the technology. I will report on these 3 generations of IMUs, BMI 055, BMI 160, and BMI 260. You may wonder what BMI stands for. So the B stands for Bosch, the M for micromechanical, and the I for inertial. And then the numbers just denote the different generations of these sensors. Let us start with a general overview of the product and packaging concepts of the 3 IMU generations. All sensors are packaged in an LGA housing, starting with a footprint for the BMI 055 of 3 by 4.5 mm, and then followed by a very significant shrink of 44% to 2.5 by 3 mm, which since then is sort of the industry standard for IMUs in the consumer electronics market. Because it has become an industry standard, we kept that footprint of 2.5 by 3 also for BMI 260. It's very important for many of our customers to have pin-to-pin compatibility in order to have a second source option. These packages are probably not very exciting from the outside, but if you look inside, then things turn out to be quite interesting. As you can see on the lower left, in the first generation BMI 055, there are still 4 chips, 2 ASICs and 2 MEMS dies, with the ASICs arranged on top of the respective MEMS. Then in BMI 160, we took the first step towards functional integration and used only 1 ASIC instead of 2. You can see in the electron microscope picture in the middle that there's 1 combined ASIC mounted on the LGA substrate, and then there are 2 separate MEMS dies for gyro and Axel on top, and they are wire bonded to this combined ASIC. Then in BMI 260 on the lower right corner, we made the next step in functional integration. We also integrated the MEMS onto 1 chip. This chip has separated cavities for gyro and the accelerometer. I will come back to this later. So just 2 chips, 1 MEMS, 1 ASIC die left in BMI 260. There were not only significant changes in the packaging and integration concept, but also in the system concept, especially in the gyro. The BMI 055 concept was derived from automotive sensors, which were developed several years ago. You can find some information on this in the paper shown on the upper right corner. As you can see in the table, BMI 055 has a closed loop architecture for sensing, which means that there is a force feedback on the sense electrodes so that they are basically not being displaced in sense direction during operation. Next topic, drive and sense mode are operated mode matched. This means that the resonance frequencies of drive and sense are the same. Moreover, included in BMI 055 is an electromechanical quadrature cancellation. For the next IMU generation, BMI 160, the decision was made to switch from the closed loop mode matched concept to an open loop mode split concept. So there is no longer force feedback to the sense electrodes, and sense and drive modes have now slightly different frequencies. And finally, we have no longer electromechanical quadrature cancellation in the system. Why did we do this change of system concept? Well, first of all, of course, it's a reduction of system complexity. We have several control loops running in parallel in the BMI 055, and that doesn't come for free, for example, in terms of current consumption. We succeeded in lowering the current consumption from 5 milliamps to less than 1 milliamp for BMI 160, and then made another step below 0.7 milliamps for BMI 260. Then there were other aspects like superior noise figures for high bandwidth or low latency applications, less complex ASIC process, and smaller die areas for ASIC and MEMS, which also help to reduce the package size. Now let's dig a bit deeper and have a look into the gyro MEMS structure of BMI 055. You can see here how the drive motion goes on the right side with finite element simulation, and on the left side in a movie of a real part in operation. One important statement is that if you want to keep the system complexity of a 3-axis gyro at a reasonable level, it is very important to have a common drive mode for the 3-axis, and this is achieved in this kind of design. There are comp drives at the very top and the very bottom of the structure to apply drive forces at the drive resonance frequency. As you can see, there are several masses connected to these comp drives. The comps and the connected masses are moving up and down, and then because you need for a 3-axis gyro 2 different directions of the drive motion, the up and down motion of the comp drives is transferred in the masses on the right to a left and right motion by using a proper frame and spring design. And of course, a 3-axis gyro needs 3 sense modes, which are shown here in these movies. You can see that these 3 motions are very independent of each other. So there's an excellent decoupling of the 3 sense modes, which means, for example, that there's no crosstalk or cross-axis sensitivity to be expected. When we started to develop the second IMU generation, BMI160, which was the first generation of low-power IMUs, one of the major goals for the design guys was, of course, to shrink the die area to drive down package size and cost. And that was achieved by a very significant amount, namely by 40%. There were several measures that we applied to achieve this size reduction. The major measure was to combine the 2 separate sense masses for omega Y and omega Z, which are marked blue and yellow on the left, which were separate in the BMI 055 into one single structure. So for BMI 160, we have a combined mass which can move both out of plane for omega Y sensing and in plane for omega Z sensing. Beyond that, we reduced the number of springs, and we also omitted the quadrature compensation electrodes. Overall, we got this nice 40% shrink. Here you can see the 4 relevant modes of this gyro. The drive mode is on the upper left. In principle, it looks quite similar as we've seen before. There's now 2 sense modes for omega Y and omega Z associated with the left sense masses. For omega Z, the sense motion is to the left and right, and for omega Y, it is up and down. Then we still have the separate structure for the omega X detection. We were a bit nervous when they did this design about possible negative effects of the combined sense mass. If we might see, for example, a significant increase of the cross-axis sensitivity between Y and Z axis, but that turned out to be not critical at all. Then the story continues when we switch from the second to the third generation of IMUs. Again, there was a target to significantly shrink the die area. My colleagues did this by another impressive almost 50% shrink of the gyro core. Here we have now a somewhat different topology because the drive direction is different, as I will show you on the next slide. But in general, there is still a common sense structure for 2 axes and a separate structure for the 3rd axis. This new topology has once more fewer springs than the previous design to save some space. Then the technology guys did a good job in reducing process tolerances, and that also allows you to shrink the sensor core quite a bit. And finally, we have an additional polysilicon layer that is being used here as a second wiring layer for electrical connections. And all that together brought us this great size reduction of almost 50%. And here again, the 4 modes of the structure which are relevant for operation. You can see that the drive mode is now going into the left and right direction. For the sense modes, we have again a lateral motion of the left masses for omega Z detection. This motion goes now up and down, and an out-of-plane motion for the omega Y detection. The sense masses on the right for omega X detection have a rotational excitation in the drive motion, and accordingly they start to move as a rocker structure when an X rotation occurs. Overall, when we now compare the size of the 3 gyro generations, we see that from the first to the third generation, we made a huge shrink by a factor of 3.3, which we think is quite impressive. With this shrink, the gyro structure of the BMI 260 is at the moment the smallest mass-produced 3-axis MEMS gyro available. You may expect that when the sensor core becomes so much smaller that performance has to degrade quite a lot, but that's not necessarily true. You can see on the left some noise figures, the noise spectral densities of the three products, which are quite comparable and have even become slightly smaller from generation to generation. On the right, you find some typical values for the bias instability of the three IMU generations. There you can see that the BMI 055 with values of 2 to 3 degrees per hour is significantly better than the successor generations BMI 160 and 260, where we obtain values from 3 to 7 degrees per hour, which is still a very decent level for a consumer device. In this parameter, we really see the advantage of the more complex closed loop, mod-matched, and quadrature compensated concept of the BMI 055. Okay, so now let's turn to some technology aspects. I showed you on the first technical slide that the BMI 260 has an on-chip integrated accelerometer and gyroscope. And as you know, gyroscopes typically need low cavity pressure to operate in the best possible way. For example, you want a rather high quality factor of your drive mode to achieve a sufficiently large drive amplitude. Whereas accelerometers need some damping and therefore need some higher gas pressure inside the MEMS cavity. There's different options how to achieve these different cavity pressures, like use of a getter material for the gyro cavity, or having different cavity volumes and different outgassing sources for gyro and accelerometer. But we decided to develop a new in-house process, which we call laser reseal. My colleague Holger Rumpf will talk about this in greater detail tomorrow in the invited talk in the Sensors in Industrial Practices 1 session. So if you're interested to hear more about this, please listen to Holger's talk. Here, as a little advertisement, I will give you just a short glimpse on the process flow. First of all, you set the desired cavity pressure of the accelerometer during the wafer bonding process of the MEMS wafer and the cap wafer. Then you do a deep reactive ion etching through the MEMS cap in the gyro region to form a narrow vent channel. Afterwards, you pump out the gyro cavities to the desired gas pressure in the gyro. And finally, and that's the most remarkable step now, you close these vent channels by a pulsed high energy laser beam. So you melt the silicon material at the top of the vent channel. You get some recast of silicon, and this recast is perfectly leak tight afterwards. Overall, with this method, you can include very low, well-defined and stable cavity pressures for the gyro. Another technological advance that we made in the last years is the introduction of the dual-layer micromachining process. In our former standard process, we just have a thin polysilicon layer for wiring, and then we deposit and structure a thick polysilicon layer in which we define the typical MEMS structures like movable masses, springs, electrode fingers, and so on. And some years ago, I showed this at the IEEE MEMS 2017, we introduced a dual-layer micromachining process where we have now an additional polysilicon layer in between this thick function layer and the wiring layer. And that opens up a lot of opportunities in MEMS design. If you're interested in the detailed process flow, please have a look at the paper in the top right corner. What you can do with this is shown on this slide as an example for a Z-Accelerometer in form of an asymmetric rocker structure. On the left, you see standard Z-axle topology where the central anchoring, some torsional springs, and a mass asymmetry with respect to this torsion axis, which provides mechanical sensitivity when a Z acceleration occurs. Underneath the movable structure, you have detection electrodes to sense capacitance differences when the rocker structure starts to rotate around the torsional axis. On the right, you see in contrast a new Z accelerometer topology that we built with a dual-layer micromachining process. As you can see, we are now able to construct more complex sensor topologies. For example, the movable mass is now built from 2 different layers here. We can also introduce top electrodes in addition to the bottom electrodes, which gives us a larger signal and allows us to shrink the sensor core quite significantly. But most important, we become in this topology quite insensitive to mechanical stress, which mechanical stress is often a source of large offset errors, especially in low-cost mold packages. So in consequence, the offset stability of these devices is quite significantly improved, and that is shown on the next slide. Yeah, you see as an example the offset versus temperature of the Z-Accelerometer of BMI-160, which still has the standard design, in comparison to BMI-260, which has the improved sensor topology made from the dual layer process, as shown in the SEM image on the right side. The data shown here include the drift after soldering and the temperature dependence of each 80 parts. As you can see, the overall offset performance, both solder drift and temperature dependence, has become much better, roughly by a factor of 4 for the new topology. So this was the technical part, and to conclude my talk, I would like to show you some factors that I think are very important to be successful in the consumer electronics market, and I also give you some outlook on what we think is important in the future for this type of sensors. If you ask somebody what's important to build a very good MEMS sensor, then probably most people respond, okay, you need excellent MEMS and ASIC designers, and you need to have a very good technology base with stable, flexible, and proven processes. So that's definitely right, and you can see most of these things in the final product. But it's not sufficient. Beyond that, there is a lot of other capabilities and knowledge in different areas which you typically do not see in the final product, but which are nevertheless essential for industrialization and market success in these high volume applications. Some of these capabilities are listed on this rather busy slide, but the list is not even claiming to be complete. For the sake of time, I'm not going in detail through this list, which covers various key competencies from product management to engineering and operations. But all these topics together listed here tell us that you definitely need a very large team with expertise in a lot of different areas to be successful in these markets. So finally, as an outlook, what do we think are the most important market drivers for future consumer electronics motion sensors? I've listed here several criteria on this page, and on purpose did not do any kind of ranking because I think that's not appropriate for these diverse applications that I've shown you in the first part of my talk. It's quite sure that cost plays a very important role, especially when the volumes are extremely high. But there are applications and use cases where other things are similarly or even more important. It can be robustness in new use case applications, or it can be ultra low power, for example, for IoT applications. It can be size. Think about hearables and the limited PCB space inside these devices. In AR/VR applications, performance is really a driver, and for other applications, it may be improved smartness or connectivity. So from all that, it becomes quite clear there will be also in future very demanding requirements, and the high innovation speed that we've seen in the past will certainly continue. And as the list of topics also shows, some of the trends are at least partially conflicting. That may lead to an increased product segmentation such that you may have dedicated motion sensors for different applications and not only one platform that basically tries to serve all different needs at the same time.
And with these remarks, I would like to conclude my talk. If you want to know more about our sensors, then there's different sources of information listed on this page. And of course, you may also simply drop me an email anytime. Next time, I hope to see you face to face again, healthy. And thanks for listening and watching, and goodbye.